everyone. My name is Ghosh and I am working as a scientific researcher at Materials and Mechanical Engineering Center for Atmospheric Research University of Bernd. And that work has been conducted in collaboration with Institute of Physics and Material Science of University of Vienna. And the list of co-authors listed here. So let me quickly summarize what is very high cycle fatigue. So the materials, if survive more than 10^8 till fracture, that typical regime is called very high cycle regime. And mainly in case of high and mainly advanced high strength steel, we observe that the materials fail even at a stress level below the endurance limit of the materials obtained through conventional fatigue testing result. And so now there is a question that is there any very high cycle fatigue limit exist or not. So of course for that we would need to investigate more than 10^10 cycles, and that you can imagine it's quite time consuming job and we need a lot of time. And if you think about to conduct this kind of test using servo-hydraulic fatigue equipment, so we know that maximum we could apply 100 Hz in case of servo-hydraulic equipment, and it would need 3 years time to complete one particular condition. So thanks to the ultrasonic testing facility where we can attain this 10^10 cycle within 6 days. So so these are certain complexity. Now for today's presentation, I just selected 2 different conditions. Can you go back? Yes, so I have chosen these 2 different grade steel. Of course, both are medium carbon steel, but the difference is one is have the slight high level of inclusion, and another one have almost negligible or less fraction of inclusion. And both has been treated differently. So first one is treated as a direct quench. Direct quench means we have conducted thermomechanical processing and followed by quench down to room temperature. And in second case, we have conducted thermomechanical processing and then quench down in between the martensitic start and finish temperature in order to attain certain fracture of written austenite and martensite combination. And then heat treated at slightly higher temperature for a longer duration. And the reason behind this heat treatment to enable the enrichment of carbon from supersaturated martensite to austenite in order to make the written austenite mechanically stable at room temperature. And of course the mechanical property also have investigated. And in case of direct quench variant CK45M steel, the yield strength was in the range of 1600 megapascal and UTS was more than 2 gigapascal. It's in the range of 2400. Of course, the ductility level was quite poor and the written austenite fraction was around 4%. Whereas in case of DQ&P variant, it has the yield level in the range of 1000 MT together with around 2 gigapascal UTS and 13% elongation, and the written austenite content was around 12. And then the microstructure of CK45M steel mainly consists martensite matrix. And apart from this martensite, we observed there is 2 different type of inclusion. One is slightly elongated shape and another one have a spherical like structure. So based on ETS analysis, we confirm the elongated shape specimen. This elongated shape inclusion is mainly manganese sulfide, whereas this spherical shape inclusion is mainly aluminum and calcium oxide. And as I said, this CK45M steel contain only few fractions of written austenite, so we can see that the film-like written austenite mainly exists at the interlath boundaries. And then in case of DQ&P steel, we can see a high fraction of written austenite present and mainly located at interlath region. And then And then we have investigated slightly more under TEM, and then we observed there is two different kind of precipitation occurred in this direct coincident partition steel. So based on TM analysis, we identified there is mainly two types of precipitation occurs. So one is transition carbide, another one is cementite. So mainly it was transition carbide precipitate, and a few fraction of cementite also present in the microstructure. And also have investigated, I don't know, for some reason it's not showing full structure, but this based on APT, we have also cross-confirmed this TM result, and we know that the stoichiometric ratio of both these carbide is different. So if it, in case of AP2C, it should have around 31 atomic percent. In case of AP3C, it should have 28, and that has been cross-confirmed through APT analysis. And also another interesting thing we observed based on APT. So here you can see this less carbon regime is the martensitic phase, and the high carbon enriched regime signify the return austenite phase. And here you can see the carbon is not distributed homogeneously throughout the return austenite. So mainly the carbon enriched quite high at the interface regime, and it's slightly lower within the matrix. So that may be due to the dislocation and enrichment during thermomechanical processing that to some extent hinder the carbon partitioning within this return austenite, but not much. And so finally, when we have conducted the very high cycle fatigue in both conditions, so here you can see, despite of having very high yield strain, these materials survive 10^10 cycle with a strain amplitude only below 650. Whereas in case of DQ&P steel, although the yield is slightly lower as compared to this CK45M steel, but still this material survives same number of cycles with a stress amplitude much higher than this CK45M steel. In this case, it is in the range of 750. Now, when we check the failure mechanism, so in both conditions, we found that the materials failed from the interior inclusion. So in this condition, DQ&P variant steel, we assume that this steel may not have significant amount of inclusion. Still, we see that these materials also failed from this very tiny interior inclusion. So, and also another thing, we observed that near to this inclusion, there is a fine granular bright area present both in this condition and also in this condition. So, in order to further investigate the micromechanism associated with this failure, we have investigated this certain condition. So, we have just selected this particular this specimen which failed after this 10^8 cycle, and then we just prepared the fib or lifted out the fib specimen adjacent to this failure region, and then when you see this specimen under TM, so we clearly see the fine granular structure formation, and this we measured based on selected negative fraction, and also in different axes we measured, and then we assumed the diameter of this fine granular area is near around 1-2 micrometers around the inclusion. And then you can see that that after this design, there is no such granular area exists. So it's only twin martingale present. So this is not surprising because twinning martingale generally observed in medium carbon steel, and twinning martingale occur in order to accommodate the plastic strain. So as I think Professor Chai also discussed this modeling. Now still it's quite confusing because a lot of people assume different phenomena. So in our case, I assume that this could be the probable mechanism that during the cyclic loading, first crack initiation occur adjacent to this inclusion, and then due to continuous application of cyclic loading, there is an interaction between slip bands and triarsonate gain boundary, and then it's finally martingale fragmented into fine granular grains, or it's fragmented into nano refined grains. But recently, not recently, but I also want to mention this thing that Murali also claimed different mechanism. He assume that hydrogen may enter into the specimen during processing time, and it may trap adjacent to the inclusion, and this hydrogen may have significant influence on this fine granular area formation. So for this we need further investigation that I am not going to show for today's presentation, but we are working on this topic. So we are now planning to investigate this under hydrogen charging condition. So next, another thing I want to show that for my own interest, I wanted to see how the artificial defects affect the fatigue property. So we prepared different diameter drill, and then we measured the very high fatigue property, same condition, and here as expected, depend on the size and shape of this artificial effect, the fatigue limit significantly reduced down. And one more thing I want to highlight here. So it was well known that if there is a crack initiation, so then it would propagate drastically and there will be failure. And as per the definition of fatigue limit, we assume that if fatigue limit means what? The threshold limit where there may not be any crack initiation or crack propagation. For example, if we apply certain load here, so materials may survive long life. But based on this analysis, so this specimen we observe that in this condition, when we apply 625 MPa stress amplitude, and when it's ran already 10 to the power in the range of 10 to the power 10 cycle. So after that we observe there is a tiny crack initiation adjacent to the inclusion. Then we want to cross check if there is any crack propagation or not. So then we perform another set of 10 to the power 10 cycle. So that presented here. So here you can see there is no difference or very tiny difference. So that's further think twice to modify the definition of the fatigue limit. So fatigue limit, we can say the definition of fatigue limit, we can say that it's kind of threshold limit of crack initiation, not the crack propagation. And one more result I am to show. So here we have also performed the near threshold fatigue crack growth test in different conditions. So first one is under air atmosphere, second one is under vacuum, and third one we perform the another separate tempering treatment at 100 degrees centigrade for 1 hour. And here you can see when the test has been performed under vacuum, then fatigue crack growth resistance improves slightly. So that promotes the assumption that normal air may act as a corrosive environment. So that is the reason when we have performed the test under vacuum, we see there is a slight increment or slight resistance in the fatigue crack growth. But in case of tempered condition, interestingly, we see there is no crack growth below this temperature minus 12 cycle. So that further indicate there may be some other factors. So one could be that the hydrogen improvement could be another reason behind this improvement. So here we measured the dissolved hydrogen content. It was 1 ppm in case of H direct going condition, and after tempered treatment it was 0.6 ppm. So then when we check the fracture surface, so here we see that last time. So here we mainly see that there is an intercellular facet present in case of H2N gradient, whereas there is no any intergranular or transgranular facet present in case of tempered condition. So it's mainly ductile type of failure. So based on that also directed towards the conclusion that overall hydrogen improvement may have the effect on it. So after tempering treatment, maybe some amount of dissolved hydrogen eliminated. So that for the reason behind this improvement. So that's it. So I like to thank collaborator, DQ Institute and Center for Advanced Research.
Thank you very much.